Good morning, everyone.
Yeah, good morning, sir.
Good morning. I'm sorry, it's raining here, so my hairs are all messy. I just came from outside. Um, all right, let's start. Okay, I think it's just you, Rajesh. So let's wait for some time.
Hello, Santan. Good morning
Good morning. Good
and
morning.
happy Teachers Day too.
Thank you. I will start in a minute or so. Uh, yeah. Okay, let's do pre-processing on the same data. Let's do it on the screens. Guys, we'll start in say 2 more minutes. I want at least 3, 4 people to be there. Oh, there are 4 people already. So yeah, we can start then. Okay, so today we are going to learn how to structure data. So essentially, how do we, I mean, so if you look at NLP data, right, this is unstructured, like English text, it's not given in a proper tabular format, right? So how to put everything in a proper structured format. Okay, we have seen that yesterday for some part, but we will see some advanced techniques. So these are the different representations that we have to work with. One of them we have seen, which is called as bag of words, where you essentially put in like every feature or every word as a column. Okay, so I'll just give an example. So let's say if this is the data, this is a data set from Kaggle. So here we have some tweets. Okay, so in this text column, let me just do a head of this. Yeah. So in this, there is a text column. Here you have the tweet. So I'll talk about this data set a little. So the idea is when airline passengers, okay, when they deboard, like when they arrive at their location, they typically send a tweet about the experience or if they liked something, right? So these are tweets from those passengers upon arrival, and somebody has done a little bit of analysis. So, for example, what airline it was, okay, how much is this? What is the sentiment? Is it neutral, positive, negative? So somebody has already given the labels, and these labels have been given manually. What was the tweet ID? And there are other things. For example, what time zone was there when the tweet was released? When was the tweet created? And other things. Okay. So this data is given to us. We have a total of how many? Sorry, I haven't saved it yet. So we have a total of around, no, I just saved it into what? My
Head.
bad. Yeah, my bad. Okay, just a second. So a total of 14,640 tweets. Okay. All right. This is the number. So I'm going to show you this text part because that is what we'll be dealing with. So this is the text part. Okay. So this is where the tweets are there. So these are your respective tweets. Okay. So the thing is, we have to convert this data into, say, a structured data set into a tabular format. And you can see that, like, if I show you the first tweet, let's say the first tweet, this is only this much. If you look at this first one, this is a little different. This is a little different. So if you think about it, it's not given to you in a tabular format. So what we have to do is we have to convert, because machine learning algorithms work with numbers. They don't work with the text. So you have to essentially convert each tweet as a vector of numbers, okay, as a vector of numeric values. So one idea is I figure out all the unique values, and if the word is present, I put a 1. If the word is not present, I put a 0, right? That is what we have seen already, and we have used a function called as transaction encoder for it. Yes or no? Do you guys remember? We have been using it quite frequently, right?
Yeah.
Okay. Now, please note this. This transaction encoder works. So the input to this transaction encoder is a list of lists, okay, or an array of lists. Basically, a collection of lists. Okay, this is necessary. So, do you want me to do this again and then go to advanced techniques, or you guys can do it on your own? What do you recommend? Can I do it?
Using the
one more time?
transaction encoder, right?
Yeah, using the transaction encoder on this type of data. Shall I do it?
Yeah, can you? Yeah, do it once.
Yeah, sure. Okay. So one thing that we'll do is we'll take these tweets. Currently, they are in, I mean, if you think about it, they are a collection of strings. Okay. So you can say this is a series of strings. I want to make it a series of lists. So I will use this. And one idea is I think we have discussed this before yesterday, that you split it by
commas.
Spaces.
Yeah, sorry, spaces.
In this case. Okay, so you can do this, but there are flaws with this approach. That's why we have seen this yesterday. So we will use word tokenize for this. Okay, I'll use word tokenize for this. So let's use this word tokenize. So essentially, I'm going to parse these strings one by one. Okay, so I'm going to parse these strings one by one. I'm going to first convert everything to lowercase. Okay, I'm going to convert everything to lowercase. Okay, maybe I'm going to strip this at the rate. Okay, I'm stripping this at the rate. Okay, I'll just replace this. That would be nice. Oh, but it will replace. Okay, because it's a string, it will replace everything.
Yep.
All right, I'll replace with nothing. Okay, just a second, it's not working. It will replace only at the rate. Okay, so what I'll do is I'll do left strip. No, but I think if it starts with it, then it will be stripped. 1 second. So this is not there. I'll just try strip. No, there is a left strip and a right strip. Okay.
Yeah, in pandas.
Oh, sorry, I'm using it incorrectly. I have to use the string property first. Now this is L strip here. 1 second, it stays. Okay, I mean, you don't have to pass this. Okay, you can see that it has been stripped. Okay. See, it's a series, right? So I have to use this str property. Otherwise, you can directly, so if it was a string, so let's say like this, then you can directly strip. So let's say if it was like this. So taking maybe say the first string. This is the first string. Now it's a string, right? You don't have to, so you can directly strip this at the rate if you want. Okay, so it will strip it from the left. Okay, but there are words. So I will actually do this. Okay, when I'm passing this, I will strip this at the rate. Okay, I will strip this at the rate. Anyways, I'll use this. I'm going to tokenize these words. So this is my data. I'll take each data sentence by sentence. So let's say for each tweet in this, what you do is you give me the tokenized version of this tweet. So this is each tweet. And I will append it to my data. Let's call this as data. Or you can call it, say, tokenized tweets. So we will append these tokenized tweets to the data. Okay, now that I've appended it, what I'll do is, see, once I've appended it, I'm going to run a simple for loop. Okay, let me check the brackets. Yeah, brackets are fine. So I'm going to run a simple for loop, see this. So maybe say for each word in tokenized tweets, that would be a string, right? If you think about it. So you will first get this
Yes.
Virgin America, then what, then @. So I'm going to strip each word with @. Okay, I'm going to strip this @. So again, what you can do is each word. So let me say once I get these tweets, I say that, okay, my list is L. Okay, so I don't append this here. Okay, just a second. I'll say, okay, give me this. Okay, I'll put it here. So this will give me all the individual tokens. Now what I'm going to do is I will take individual tokens and I will apply this L strip to it. Okay, let me strip this @. So we strip everything and then we append this to L. Okay, and once this whole thing is done, I will append everything to this tokenized tweets. Does it make sense? So what I'm doing is first I'm tokenizing this. It will break it into, say, Virgin America, then what, then this D Hepburn, then SAD, then SAD, then SAID. After this, what we are doing is we are looking at each word and seeing if @ exists in the front. Okay, if @ exists in the front, it will just strip it. Otherwise, it will return it as it is. Okay, so that is what is being appended to L. Once everything is done, I append the whole thing to this tokenized tweets. So this whole thing, when @ is removed, this will be appended to this tokenized tweets. Okay, let's see this. It's running for all of them, 14,640 tweets. Okay, let's see this. Okay, this is your tokenized tweets. Okay, so there are some empty brackets. Oh, that can be removed. There is no issue with that. Okay, does it make sense? You see
Empty white
@
spaces.
well, that is coming because you might have like when you are stripping, right? It adds a space there.
Yeah.
Okay, that's fine though. That's fine.
That empty spaces and the full stops will not do anything to our
We
analysis.
will remove the stop words. We will
Okay.
remove the stop words.
Okay.
So let's say we import the stop words. Let's instantiate the stop words. And we need only English stop words. Okay, and then I'll run a simple for loop. So let's say for each tokenized tweet in this tokenized tweets. Okay. What I'll do is I'll take this each tokenized tweet. Okay, go to the length of this. So for each word in each tokenized tweet, I'll simply see if each word, this not and you can say SW in the stop words. So then I will just take an empty list. Okay, 1 second.
You said length of this, right? What you have?
Okay, just a second. Well, it will not even matter because see, depending on how many words are there, it will take them one by one.
Take that much of iteration. Okay.
Yeah, you don't really have to, figure out the length and then index it. That will be like expensive. Okay, let me say I'm appending this into L. So I'll put the tokenized, basically each word. If it is not a stop word, I'm appending this to this L. So this will have all the stop words removed. And finally, let's say I will say data without stop words.
Top
Okay.
words.
So I'll just put the data without stop words here. And I append this to L. Okay, all right. I just have to check one thing. Yeah, I need to append a few special letters or special characters to this stop words list. So maybe say space, the empty space, and then a single space. Maybe say a comma, a dot.
Dot.
Okay, let's say exclamation mark. Let me put, okay, the exclamation mark is fine. Then you have question mark.
On the dot, one.
One is missing. Okay, okay, let's say this at the rate, let's say somehow it's there. Okay. This star, say hash. Maybe these left brackets and right brackets. Okay, I think this is more than sufficient. Maybe I'll put a dollar also because we saw dollars yesterday in some. Okay, so I think this is fine, more than sufficient. So yeah, my bad. Okay, so it's done. Let's see data without stop words. So you can see that like stop words have been removed. So like what was there that has been removed? Yeah, obviously there are like dot, dot, dot. If you want to remove dot, 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 you can put it here.
We need to add it, yeah.
I mean, obviously it's going to take a lot of manual time because you have to figure out every time. Okay, so like this is their exclamation S. So you can put it like this here. This will be removed. If you see anything else like this, have short form. Okay, anything else that you see?
Not.
Looks like not. See, there is this colon also. So, I mean, it will take a lot of time if you go through every tweet. So I'll just stop here. I mean, if you want to be, what we say is, I mean, really careful. Okay, you can go and, okay, I'll just remove these at least. Just a second. Yeah. See, the more you ensure, the better results you'll get. This is 10% also. I don't know that. I'll just stop here. Okay. Still a semicolon. At least on the things that I'm seeing, okay, there shouldn't be anything. Okay, there's this double.
There is a lot were coming. The people were tweeting is like easily tweeting.
No, it takes time. It takes time.
Yeah.
That's why this manual thing is.
But when it comes to the okay, so we were working on the 14,000 data sets. Like when in real time, if I'm working on NLP and I'm founding this kind of data, on that time also I need to do all these prerequisites before I'm beginning. Okay.
Yes, if you want to construct your features, so you have to do all this before. Yeah. All right, I've tried to remove some of them. Okay, and at least here you don't see anything.
Yes.
Okay, so now I'm going to convert this data to say a structured representation, a tabular representation. We can do this with the help of a transaction encoder, which is there in MLXtend. In pre-processing, let's import transaction encoder. Okay, and let's say this is some PE, and then we fit to our data, which is data without stop words. So if you fit it to this, you will get all the unique columns, the unique words. So these are all the unique words. I should have removed this percentage also. Okay, but anyways, you see these are all the unique words. There are a lot of these, what we say URLs also that could be removed. Okay, but I hope you get the point. Okay, there is something that like this dot and this. I could have stripped this dot also. Just give me a second. So there is this something dot with this. Okay. Do you see anything else that I construct before? All right. Doesn't seem like it. No, that's the only thing. Okay. So you'll not see those dots at least. Okay. You'll not see those dots at least. Okay. Anyways, this is fine. This is done. So let's so let me just run this again. So these are your columns. Just a second. Why is this dot coming here? We just removed it, right? Just a second. This dot WE. I stripped it, right? Give me a second. I just stripped it. Oh, I should have stripped it here. I should have stripped it here. Okay, 1 second. I have to think. So I've already done this. I have to run it one more time. Okay, I have to run it one more time. If I want to strip dots, you have to run it one more time. I have to strip dots. Basically, I need to create a list. Okay, like this. So for let's say I'm going to remove some. So let's say these are the stripped tokens or stripped characters. Okay, so this is what I want to strip. I want to strip @ and I want to strip say this dot. Okay, so what I'm going to do is for basically you have to run it for each strip character. Okay, here what you have to do is so first strip this, okay, @ so you will get basically a string again, and then you strip. Okay, shall I do this like each char 0? I can do it like this. For L dot append, else dot strip here, I can say each char. Okay. So after this, each word is stripped using this. Okay. I'll put it back to say 1 second. I have to think. Okay, what should I do here? Let's say this is my W word, and I will say this W is going to be appended to my list L. So L dot append this W. So once I've stripped everything, this gets appended to L, and then this tokenized tweets have this L. Okay, makes sense. Okay, let's see this. Hopefully, I will not see that dot thing anymore. Okay, let's see. It will not be here. Let's maybe here. I could have removed this percentage sign, but anyways, that's fine. Let's see if you have these dots anywhere in the beginning.
It got stripped.
It got stripped, I think. Otherwise, there are pluses also, minuses also. See, that's why you have to do all these things. Okay, you can put a plus there, a hyphen there in the beginning. Okay, a lot of problems with text. So you can put a plus here. Okay, you can put a minus here.
Minus, hyphen,
Uh,
underscore.
I mean, you can just strip like each of these words. Anything else that you see? But see, if you strip this hyphen, right, then the smiley, some people have made like this smiley. This would be lost. So these things are like quite tricky. That is fine. Anyways, okay, I'll stop here. Let me start. I'll just strip these two things here as well. So this percentage, and I saw this slash, and there was one more thing, which was this hyphen. I'm going to remove this hyphen, and there was this underscore, underscore, and an underscore. Okay. All right. So let's just run this. Run this again. And this again. Okay. So all this is done. And see, I can put an exclamation mark in front as well. And also, this is where I can keep on going. This exclamation mark is there. This post office is there. Everything else that you see, that's it, right? This hyphen also. Okay, I'll do this as well. One more thing I'll do. Okay. Is this a special hyphen and is this a special symbol? Okay. What I'll do is I'll check for these. Okay, I'll check for these. So what I'm going to do is, let's say that, okay, for each word, okay, after stripping, if your the first two letters of the word, okay, so first two letters would be this. If they are equal to this, I don't want to append. Okay, I don't want to. If this is not equal to this, then I want to append. Okay, then I want to append. Does that make sense? See, you will not see these URLs in that case. So I'm saying that if a word is there which has these double backslashes in front, so this should not be appended. Hopefully, this should be removed. Okay. Let's see. Yeah, a lot of numerals are coming. Okay, but this is not getting single quote. Okay. So single quote there in my initial, it is there, right? Single quote is there. It looks like a different character though. Okay, anyways, that's fine. Let's see if those things have been removed. Yeah, do you see that all URLs have been removed? Do you see that there were those backslashes, right? All of them have been removed. Does it make sense?
Yes, Anton.
Yes. Yeah. But then these pluses are not being removed. I don't know why. Do I have a plus in the beginning here? I do have. Is it a special plus? Because see, sometimes formatting can be a problem. Okay. That's a plus. This plus plus. I'll take this plus and let's see. Looks the same, right? Is there any difference? No, it doesn't look like it. Okay, this is fine. Do you want me to remove some of the numerals also? That can be done also. Okay, all you have to do is this. Okay, maybe say create a range. Okay, So let's say like this. So we are going to create a range, say starting from say -100 to say 10,000. Okay, and it'll just take some time, and you can convert it to a list. Okay, and then you extend it further. Okay, so you can say sw.extend. So some of these words that you're seeing, that will be removed as well, like 23 and all that. Does it make sense? So
Yes.
numerals will be removed as well. Okay. Okay, let me just run this again, and I'll stop here. Okay, no more doing this further. Okay, I hope you don't see any. No, there are some new. Okay, but then there is this star here at the end. Some this exclamation is there. No. There is this. This should have been removed, right? 1119. Why not? Do you see any special characters here? We have gone up to 10,000, right? Yeah, we did. We did. So I see 11 and then I see 11 dot again. Okay, anyways, but some of them have been removed. Okay, there are dates. You can see there are so many issues with this. But numerals are not getting removed. Just a second, please. Just a second. What is my SW? We should have a lot of these. Yeah, this is having a lot of numerals here. Okay. So I'm running this. I am checking if it's not there. Okay, one thing that I can do is, but for numerals, this shouldn't matter. Just to make it precise, this shouldn't matter. Anyways, this is more than enough. I will try to figure it out, okay, why this is not working cleanly. Okay, the idea is you remove all the unnecessary things. Okay, once these unnecessary things are done, you can see, okay, this is the length. This is the number of unique values, 15,709. These are the number of features that are there with you. Okay. So now you can transform your data. Transform, and you can do this data without SW here. So this will transform it, you convert it to integers. Okay, and if the word is present, it will say 1, otherwise it will put a 0. So I'm going to put everything nicely in a data frame. Okay, and give the column names as te.columns. So this portion is done. My system is getting stuck. Okay. Now
There is a lot of emojis.
there are a lot of smileys that you see which people have posted. But anyways, the data got transformed. That is the important part. Okay, is this clear? The first part, like if it's a 0, the data is not present. If it's a 1, it is present. So every feature
Yes.
is of size. I mean, every row vector is of size this 15,709. Okay. And now let's say if you want to do sentiment classification, see you have this sentiment, I think. So if you look at your data frame, there is this airline sentiment. Okay, so you can use this as the output. and do your predictions, right? Yes or no? Make any machine learning classifier, train it on this, and you'll be able to, train any classifier on this. Does that make sense?
Yes.
This would be your encoded data input. This would be the output. So train any sentiment classification model. In this case, it's a multi-class problem, neutral, positive, and negative. Okay. All right. My system has started lagging. Anyways, this is fine. All right. So now I'm going to show you how do you count numbers. So currently we are just looking at presence or absence, right? We will now see, and this time I'm going to do it on a smaller subset, okay, because my system has started lagging. I'm going to do it on a smaller subset of tweets. So what we will do is, if a word is present, we will be actually putting in the frequency of the word, okay? So please note this first, this type of representation, it's called as a bag of words, because you're using the features, the words, to represent your data. So if you use it for even more representations, let's say where you are counting, okay, where you are counting how many times a word is present, that is also a bag of words, but then you are putting in the value of the frequency of the word, okay? So wherever you represent words as your features, you call it as bag of words representation, okay? Let's see how do you put frequency of the word, okay?
So instead of putting zeros and ones, if it is present, we'll put 1. In here, we'll put the frequency of the word.
Frequency of the word, yes. Okay. So if it is even present more than once, so let's say if it is present 2 times, so you'll put a 2 there.
Got it.
Okay, so, but it is still bag of words, but it's just that you are putting the term frequency, the word frequency. So let me just label it here. My system has started lagging badly.
Yeah, we can see that like your video is going a little stutter and then Zoom is ready and all those.
Oh, okay. Shall I restart the kernel?
No.
Yeah, I can restart the kernel so that everything gets lost. Okay, just give me a second. I'll just import the libraries again. There is no harm in that. Okay. All right. I'll just import the libraries again. This will save me some space. At least memory space it will save. Okay, and okay, I just need some functions. So one is the word tokenize, and I need. Okay, this is more than sufficient. I need these functions only. Okay, so what we'll do now is, come on. Yeah, what we'll do now is, let me just import the data set first. So we will use this text column, and then we will try to, I'll take the first few rows of the text, okay? I'm going to take only this much, maybe say top 100. Will that be sufficient? Yes. There's a top, it's top 100, so I'll go up to 99. So because in this case, 99 will be included, so it will be exactly 100, okay? You can see that 99 is included, so it is exactly 100. So I'm going to convert this, okay? I'm going to convert this. So you can do all the necessary steps back again. Basically remove @ hyphen and all those things. Do you want me to do those again, or shall I just show you how to convert every word to its frequency?
Just show us, like, because we have already seen it, right?
Yeah. Okay. Let's see this. So first convert everything to lowercase. That is necessary. Okay. Now we are going to see another function which is there in your sklearn. Okay, which is there in your sklearn. So let's use that. So go to sklearn dot. Here you have to go to feature extraction, because this is a feature extraction technique. You have to go to text, because there are like image feature extraction techniques also. So we are specifically focusing on text, and this is called as count vectorizer. So this will count the frequency of every word. Okay. So instantiate it. The syntax is almost the same, not exactly the same, but almost the same. So first you fit it to your data. Please note that the input to this count vectorizer is a collection of strings. Okay. So this is a collection of strings. Okay. Input is a collection of strings. You can call it, say, a list of strings or a series of strings. All right. Or an array of strings, whatever you deem fit. Okay, so first we fit it because can we see that? Okay, all are strings only. So I don't need to tokenize it. Does it make sense?
Yes.
Okay, so maybe I can strip this at least, this at the rate. Yeah. In the front. Okay, so I'll just strip this. Okay, I'll use these 100. So I fit this, okay, and it has fitted the count vectorizer. Now, once you fit the count vectorizer, you might want to see what are the unique columns. So the unique columns are there in vocabulary. Okay. Now, this time it's not a list. It will not be a list of words. It will be a dictionary. Let's see this. Okay. Does it make sense? So this is not a list of words. It's a dictionary. So you have these key value pairs. So the value that you see, this is the index number. Okay. This is the index number. Now, think about this. If I pass this to a data frame, what would be the first column? What should be the first column? It should be at index 0, right?
Yes.
This value should be 0, but is the first value 0? No, right? It's
No.
571. So if you pass it as it is, then Virgin America would become the first column, which is not right. Okay, it should be the 571st column. So the labeling would be improper. So if you want to sort this data, okay, you just type say sorted and sort the vocabulary, and it will sort it based on the values of the dictionary. Okay.
Vocabulary is in the
In this case, it is not. It's a column names essentially. So previously it was columns, right? In transaction
Yes.
encoder. Okay.
Yes.
Here it is called as, so this transaction encoder, it had a list of words. Okay, it was not a dictionary. Here you have a dictionary. Okay, so the format is a little different. But since the list is already arranged, right? I know the index 0 word is present in its correct location. Here, this is the 571st column number. So I cannot just keep. So when I'm creating my data frame, I cannot pass this vocabulary directly. I have to pass that particular word first, which is at index 0. So if you see, I don't know whether you can locate it or not. So 000 is actually at index 0. Okay, just to show you. Okay, this 000 is at index 0. Does it make sense?
Yes.
Okay, let's say if you look at 0736, which would be at index 1. Okay, makes sense? I'm looking at this and telling you. Okay. If you look at 10, that is at index 2. So do you see that now it has been sorted?
Yeah.
Okay. All right. Great. So now that the vocabulary is sorted, you can actually create your data frame. But before that, we have to transform our data. So use the transform function, pass the data which you want to transform. So this is the data that I want to transform. Now, this is a similar syntax that we have used already. Okay, so this time it's giving us a dense matrix, sorry, a sparse matrix. We have seen this before, right? In one-hot encoding. Does anyone remember?
Yeah, sparse matrices.
So we can just convert this to dense using the toDense function. I'll just write it in another line. So I'll convert it to a dense representation, basically the tabular representation. So this is ready. Let's put this in a data frame. Let's put this in a data frame. All right, so I've transformed my data, giving the column names as sorted vocabulary. Looks all right. Let's see. Okay, so the data has been put. Do you see any twos anywhere? Here it is, right? Twos are there. Okay, does it make sense? So now you're counting essentially. Is this clear? Any questions? Yes, people. Anyone with any questions about this? Okay, so there are no questions. I'll show you like what to do next. So the idea is this particular representation, term frequency, it has some bottlenecks. Okay.
So on the
But
ninth,
not bottlenecks. Essentially, it has a limitation, and the limitation is the frequency of the stopwords would be the highest, right? What can you say about the frequency of the stopwords? Words like a, and, the, or, and.
that would be pretty high.
Very high, right? In comparison to other words. Okay.
Yes.
Is it possible that you will remove all the stopwords? I mean, if I give you 1,000,000 tweets, would it, I mean, if you look at the list of your stopwords, that is just, I think, some 100 or 200 stopwords only. Okay. So frequency of stopwords becomes very high. Okay. So even if you put, say, irrelevant meta characters, that frequency can become very high. Put in smileys, they will become really, really high, but smileys might be important. So the idea is, can we reduce the weightage? See, if you look at this 2 here, can I say the weightage of this word here for the 95th row is more? Yes or no? In comparison to other words?
So, the weightage was high. Yeah.
And the weightage is high, right? So does it play this big of a role in, say, sentiment classification? Because it's a
No.
tweet sentiment. No, right? So the idea is I should reduce this value, right? I shouldn't put it as a 2. I should put it as a smaller value. So how to do this? Okay. So there is a way to avoid it. So this is called as term frequency.
So on the 95th column, the your was 2 times repeated, so that it counted as 2. But now we were going to reduce it.
Now we are going to put in some value which would be lesser than 2. Basically, it would reduce the weightage of this word.
Got it.
Okay. So this is called as term frequency, inverse document frequency. Okay. So what we are doing is we are going to normalize. Okay. Essentially, what we are going to do is we are going to normalize the weight of every word. Okay. Or normalize the frequency of every word. Okay. In a document. Now, how to do this? This is done using this term frequency. Okay. Inverse document frequency. So let me just give you the formula first. So let's say you have a document DI or a row number RI, let's say. This is row number, let's call it row I. Okay. So this is essentially a document and you have some word J. Okay. Any particular column J. Okay. So if you were looking at term frequency, okay, if you are looking at term frequency, can I say this would be nothing but the term frequency of word J, okay, in document row I? Does that make sense? Yes or no? We are actually checking how many times this word is repeated, right?
Yes.
Okay. So what is this term frequency, inverse document frequency? So let's call this as TF-IDF. Okay. So this TF-IDF of row I and word IJ is equal to term frequency multiplied by inverse document frequency. Okay. And how is this inverse document frequency computed? This is what is the most important part. This will act as the normalization factor for you. Okay. So if a word is repeated in more number of documents, do you think its weightage should be high? So it's like a stop word. So its weightage should be low, right? Yes or no?
Yeah.
So inverse document frequency is given as, I'll just mention it like this. So inverse document frequency is given as, so the name itself tells you inverse document frequency. So it is given as log of, okay, there is a ceiling function here. Okay, this is the ceiling function here. So what the ceiling function is n divided by n is the total number of documents or total number of rows, you can say, divide by in how many documents the word this word J exists. Okay, let me just write it like this. Okay, word J. Okay, word J across corpus. Okay, so here this thing means that in how many documents are basically the total number of documents in which the this word J exists. Does this make sense?
Yes.
Okay, so let's say if this word exists in every other document, what would be this word J across corpus? Anybody? If word J exists in every other document, what would be word J across corpus? It would be equal to n, right? Where n is the total number of rows. Yes or no?
Yes.
Okay. I mentioned this base is actually 10. So if n divided by n would be what?
0.
1. N divided by n would be 1. Log of 1 would be 0, right?
Yeah.
Yes or no? So
Yes,
if you
yes,
multiply any word with IDF, if its IDF is 0, what do you think the frequency will be normalized to? 0. Does it make sense?
Yes.
Okay. So essentially it's like acting as a normalization factor. Okay. This thing acts as a normalization factor. It acts as a normalization factor. Now, what some people do, okay, you need to understand this. What some people do, they will add. So imagine there is a new document coming in. Okay, there is a new document coming in. In this new document, is it possible that a new word you might see? So
Yes.
if you are having a new document, okay, so what would be the word J across corpus? It would be 0, right? What would be this value at the bottom? It would be 0 because the word has not been seen in the documents before.
Yes. Yes.
This is quite possible, right? Okay. So if you are going to make a prediction, this thing would become 0. So what is log of infinity? Again, a very big number. Does that make sense or not? So just to avoid this, what people do is they add a +1 here and a +1 here. Is this clear? So just to avoid that issue, that if a word is not present, let's give it some. I mean, at least assume that okay, it is present once. So you add 1 to every. I mean, every word initially. That's what the formula says. Okay.
Sure.
Okay. This is just done to avoid during the prediction time. Okay. If a new word is coming, so you use this formula instead of using. I mean, the actual formula, which would create trouble. Okay. All right, let's see how to do this. Syntax of this is exactly the same as this count vectorizer. You need to use this time TF-IDF vectorizer. So I'm going to do this on the top 100. Okay, so this is called as TF-IDF. So term frequency, inverse document frequency vectorizer. So TF-IDF vectorizer, let's call it say TF only. So first I fit it, and then I will, it's the same thing. You will see the vocabulary here. Okay, I'm going to sort this. Vocabulary would be the same of your count vectorizer. So I've just sorted this. And now I'm going to transform the data. So let's transform the data. So use this tf.transform. So if you transform the data, just pass this here. So upon transformation, it will give you a sparse matrix, convert it to dense. So once you convert it to dense, you can put this nicely into a data frame. So this would be pd.data frame. Okay. And the column names become sorted.tf.vocabulary. Does this make sense? Same thing as we have done in count vectorizer. I'm just showing you in one step directly. Let's see this. So this is how, do you see that now UR has been reduced?
Yes.
Okay, for 95th, it was how much, by the way, 2, right? Before.
Yes.
So it has now become around 0.32. Okay. So it will kind of reduce the frequency of the words. Okay, and if a word is repeated less, what do you think it will happen? What do you think will happen to this value? Will it increase or decrease? Let's say if a document, if a word occurs in only one document, what would be IDF? N by 1, right? Log n. If n is a lot, then log n would become bigger, right? It's a big number. Let's say n is a million. Okay, let's say n is a million. So you will be multiplying that quantity by what number? By 6. Does that make sense? Yes or no? Assume that n is a million. Okay. So million will mean 6 zeros. Okay. So 10 to the power 6.
Yes.
So log 10 of 10 to the power 6, because this occurs in only one document. So log 10 of 10 to the power 6 will give you 6, right? So you will multiply this quantity 6 with the actual frequency of the word. So you have scaled it 6 times. So important words will get scaled, and not so important words will get, you can say, I mean, their importance will be descaled. Okay, I mean, it will be reduced. Okay, so this is how TF-IDF vectorizer works. So people use this vectorization. Okay, but now there is still an issue with this. What do you think is the generic issue if you try to convert your word representations like this?
Sanatan, I didn't know.
Yes.
Only for me or anybody? You're going stutter sometimes.
Maybe the internet connection is a little weird. I don't know.
Okay.
Is it still happening?
Like often it's happening. Like for seconds, it's going. Your video is stopping and your voice only was coming out. But that did happen.
Is it happening for others also? Can somebody confirm? Is it happening for others also?
Not now.
Okay. I think it's there at your end, Dinesh.
Okay. Let me check my
Yes.
internet connection then.
Okay. Because I use a FiberNet connection here, so I am in an industry campus right now. So there, the internet connection is quite good, unless my, I mean, you can say my RAM fluctuates. Okay, then only you might see a disturbance.
Okay, maybe mine in network because I'm in a very interior village, so I'm using
that's
my
okay.
dongle and
Okay,
all this.
that's
Yes.
That's okay. So, okay, we were discussing, if you use this to convert your features, what is the major problem that you see? What would happen to the size of the structured data set? Can you imagine? Like for a very big data set, how many columns would you construct? Quite a lot, right? We just saw that, okay, with some 14,000 tweets, even after doing so much reduction, we still had around 15,000 features.
Yes.
With just 14,000 tweets. And tweets is just, if you remember, I think there is a limit on the number of words that you write in a tweet, right? I don't use Twitter, but I know there is a limit.
Yes,
What is the
there is a
limit?
I'm not sure. Let me Google it.
Anybody who knows, like 180 words or say 1,000 characters, like what's the limit? Okay, let's assume that there is a limit. Okay, so if you cannot write beyond that number, so you are restricted by the vocabulary, right? If you think about it. And even with that, we are using 15,000 features. See, just to represent a tweet of say maximum length, we are using 15,000 values. What if I make it say 5 million tweets? This number would become even bigger, because every time a new tweet comes, there is a possibility that you might use a new feature, a new word. Okay, so this thing grows exponentially as the number of examples increase.
140
I wouldn't-
characters, Sanatan.
140
and Elon
characters is
says,
even
yes,
smaller.
Elon says he is going to increase it to 10,000.
Oh, that's good. That's good. So it would be like a post. All right. So the idea here now is how to reduce the number of features. Okay. One idea is, see, you can drop like rare features, right? Yes or no? Can
Yeah.
you drop very rare features instead of saying them rare? Let's say, can we drop some of those features who were? Let me save it. Let's say these are my encoded features. Okay. So I'm going to say that if, so I'm going to show you the sum of it. Okay. So this is the sum of all the features, and I'm going to put it in some descending order. So let's say sort values, maybe ascending order. Okay. Just to show you, and let's say ascending is say true. By the way, it does it in okay. So do you see that? Like I can remove some of the features. Like see,
Yeah.
the word "the" is still getting a very high frequency. So you should have removed it before, right? We didn't do any stopwords removal and all.
Yes.
Yes or no? Okay.
Yes. Yes.
So the idea is, can we remove like really rare features? We can, right? So currently it is just 0.2177. Okay. There are a lot of these values which I believe might be 2177. Maybe say the top 100. Okay. How many are there? Maybe say 50. I mean, all of them are fairly close, but still, no, there are only a few up to this point only, like 6 or 7 only. I presume there would be a lot of numbers. But if you look at a big data set, many of them will have very rare frequencies. This number would be actually close to 0.111 something. So you can drop very rare features. That is one thing that you could do. Another is you can actually drop like really high values. Okay. So essentially the features which have a very high score, okay, they can create problems because they will act as outliers. Does that make sense?
Yeah.
Drop features with very high frequency, okay, very high score.
But
Okay.
if I'm dropping the word with a very high frequency, like in this case, we don't have filtered the stop words. But when it comes to the real time scenario, on that time, if the word was coming again and again, and I'm uh, you know not other than the stop word it's coming, and I'm just taking out of my data, means that won't cause any harm to my result.
No. See, but then if a word is being used so many times, so think of say possibilities like spam classification. So if I give you a word like, okay, you have say a bonus,
Okay.
or I mean, I'm writing bonus many times, okay, or maybe say you have won a lottery, and I stress on this fact that okay, I mean, give me your account details so that you can have the lottery amount and so on. Okay, so that will be like fake messages sent to you, right?
Yes.
Okay, so the spammers actually try to fool the system by giving, you can say, important words more frequency. Yes or no? So you have to
Yes.
take care of those cases also. So see, NLP, that's why it is so very difficult. It's not that easy. And you have to think of the rare cases. Okay. So the idea that I was trying to give is like you can drop very rare features, or you can drop features with, drop rows where features have high values. Okay. Drop rows where features have like really high values because they can skew your model. Okay. So essentially we are doing outlier removal. Okay. Essentially we are doing outlier removal. However, there is an easy thing to do, okay, to reduce the number of features to a very significant extent, and that is what we will see next. Okay, this or you can do something called as dimensionality reduction. Have I shown you the implementation of PCA?
PCA, right? No.
Where we reduce the number of dimensions? No. Okay, maybe I'll talk about this. Okay, so there are techniques. So currently, if you look at your data, how many features do we have? Okay, let's see. I'll just look at the shape of this. So you're around 617 features. So let's say you want to convert these 617 features into, say, just 200 features. So there are techniques that can help you directly project the data from 617 dimensions to 200 or 300 dimensions. Okay, so we will see those techniques. Okay, utilize, these are called as feature extraction techniques. Okay, we might see some of these techniques. They are not in your syllabus though, but we might see some of them. Okay. We will definitely see some of them for sure. Okay. So you can utilize the feature extraction techniques to reduce the dimensions. And they typically work well for text data sets. You have at least seen recursive feature elimination, right? Do you remember recursive feature elimination where we actually select a subset of the features which are important? In linear regression, or I mean, we would have done it for sure.
Yes.
Okay, so that is a way to reduce the number of dimensions, right? Number of features. So you can use that. You can use correlation to decide if two features are important or not. So those things can be done to remove it. But I'm going to show you a technique which is the best for reducing the number of features. So it depends on what type of task you are doing. Okay, so let's try to reduce the features. Okay, and this is done based on the task. So I will talk about, okay, what you should use and when. Okay, so let's say your task is say sentiment classification. Okay, assume that your task is sentiment classification. So the question comes, okay, this is my question. Let's say the words like run, running, runs, ran, do they convey, okay, let's use these three. Do they convey the same meaning?
Yes.
But if you use them as three separate words, like if I just pass the text as it is, don't you see that they will be making three unique columns?
Yeah.
Okay, so what should I do? Should I convert every word to its root? And what is the root of all the three words?
Run.
Run, right? So I can convert every word to a root word. Okay, what do you think the root of this is? Okay, discovery, say discovered, say discoveries. Okay, any guesses? Or discovering?
Discovery.
No, it's actually discover.
Discover. Okay.
So see, root is when I say a root, right? I mean, if you want a complete valid English word, there is a different technique for it. But you can see root to be a
Okay.
specific prefix. So this is from where all the words originate. Does that make sense? So root may be a complete English word, root may be an incomplete English word as well. Okay. So typically we define the root as a prefix of a word. Does it make sense? So it would be prefix. Okay. It would be prefix. So for all of them, it's discov. Does it make sense? This
So
is
even
this. Yeah.
even we can do discover that kind of English
No.
kind of
Okay.
term
So you say that,
also.
okay, I should use this DISC, right? Why not DISC? Why just COV? Because there might be other words that you can originate from DESCOV. They should hold the same meaning, right? Yes or no?
Yes.
So they are talking about like some form of, finding some new things, right? All of these words.
Okay.
So like internal semantics also need to be the same. Okay. So essentially what we are trying to find is the prefix of the word. Okay. Try to discover the prefix. Okay. Try to discover the prefix. So this concept is, or this is also called as root. Okay. Or you can call it the stem also. Okay. Some people call it stem, some people call it root. So this process is called as stemming. So stemming the word to its root. Okay. So the question now is how to implement it. Okay. So
Santan, can you
yes,
put
go
that
on.
example also in here?
I'll show you. I'm going to put in more
Okay,
examples, more and more examples. Okay. Don't
Sure,
worry.
sure, sure. Okay.
Okay. So how to implement this? So first you need to download a package called as this. What was the name for this? Just a second. Okay, so you need, I think, one is called as WordNet. Okay, and you need one more thing. I'm forgetting the name for this. Okay, one second. In my case, they are already installed. Just a second. Okay. Okay, let's see if there is any download thing that I have to see here. Yeah, this Punkt. This is the one. This is the one that you have to install. These two things you need. Okay. See, for stemming, you only need Punkt. I'm going to talk about a different technique where you will get the exact English word. Okay, where you'll get. So 1 second. What does it say? Okay, I haven't imported NLTK. So in my case, it is already installed. Okay, so it says that it is a true. In your case, you have to install it. Okay. So let's try to do stemming. So what you have to do is you have to go to this nltk.stem and you have to import something called as a Porter stemmer. So Porter stemmer is actually a quite, I mean, I wouldn't say it's obsolete, but it was developed far back. Okay, quite a long while ago. Okay, but it is still used by many people. And there is an advanced version of this. I'll also show you that. So let's use this Porter stemmer to see how do you stem. Okay, so let's call it maybe say Porter stemmer PS. Okay, so this is your Porter stemmer, and if you want to stem anything, right? So just give a word and it will stem it for you. So let's say the word runs. Okay, do you see it stems it to run?
Yeah.
Okay, let's say the word running. Hopefully it stems it to running. Okay. It stems it to run again. Okay. Okay. Let's see what would ran be stemmed to. Okay. So ran is not stemmed to run. Do you see that? So it's essentially giving you the prefix. Does it make sense?
Yes.
Okay. Let's see for discovery. In this case, it is discovery. Maybe because there is another word called as discovering, right? Yes or no?
Yep.
No, but this is discovery. Okay, so there are some changes. Okay, let's say this is discovered. Okay, so this is discov. Okay, let's go with discoveries. It would be discov. Okay. Okay, this is discoveries is actually this. Okay, this discovery and this discoveries are the same. Okay, because do you see their stem is matching actually? I think these two, they mean the same thing. So it's matching for both. Okay. So they are being mapped to this, anything that ends with a Y, they actually make it. So maybe it's using some kind of phonetics. Like the way we speak discovery, right? We don't use a Y, right? We say it's with an I. Yes or no?
Yeah. Yes.
So internally, the way it is being used is maybe with the help of phonetics. I don't know the background behind this algorithm. If you really want to study it, I mean, you have to dig into more details. But the point is, nobody is going to ask you this. Okay, what is going on behind this Porter stemming algorithm? So this is one such application that you can use to reduce the number of features. One more thing I'll show you. It's an advanced stemming technique, which is called as Snowball stemmer. It came out, I think, around 20 years ago, which is like the recent version. Okay. This Porter stemmer came out, I think, quite long back. Okay, 1 second. What's the date? Okay. One second. In 1980. No. I think 1 second. Do you see? Snowball came in 1980. Porter came actually before this. Okay, Porter might have come even before this. No, it's not mentioned here. I mean, you need to do a little bit of digging. But so Snowball came in 1980. The previous one is actually, I mean, maybe came in 1800 or maybe say 1950s or something like that. So how do you use this? You go with, say, Snowball stemmer, SP. Okay. syntax is a little tricky for this. There is a subtle change. So you will say snowball stemmer, and you have to write in the language English because it is available in many languages. So let's say use snowball stemmer. Okay, this is for runs. I'll show you subtle differences also between the two. Snowball is actually more complete. It will try to give you more complete words in general. Okay, so let's say running. Okay, say ran. Okay, maybe you will not see any differences for these. You will not see any differences for these. Let's use this discovered. It is difficult to see because I'll use a huge corpus and show you the differences between them. Okay, so let's take a huge corpus and see the differences between the two. There will be a few differences, okay, for sure. So what we will do is I'll show you that. Okay, if you want to stem, right, I'm going to take, say, an entire booklet. So just like sklearn has a lot of data sets, this NLTK has a lot of books. So what you can do is from NLTK, you can say import book. Okay, so it imports some books for you. Okay. So in my case, I've already downloaded these books. So if you want to download anything, you can simply type nltk.download and the book title. So like text 1, text 2, text 3, and so on. Okay, does it make sense? So if you want to download this book, so you will say text 1 and then it will download this book for you. Okay. All right. So which book do you want me to work with? I think you might know some of these books if you read novels and all. Has anyone read Moby Dick? It's quite a popular book. If any of you is a Christian, then you would have read this. It's the Bible, like one of the previous Bibles, like which was written, which was interpreted, you can say. Okay. Then Monty Python and the Holy Grail. There is a movie on this as well. Okay. So, like, which book do you want me to use? Which book shall we take? And I'll show you the stemmed version of each of the words in the books, and we'll try to get, okay, where the snowball and the potter are different. Tell me, which one shall we try to take?
We'll take the text one itself.
Okay, text one, Moby Dick. Okay,
Yeah.
All right. So this is your text one book. I just want to show you something. So this is your text one. Okay, sorry, it's 1 second. Just a second. Oh, okay. I have to import. I have to write it like this. Okay, 1 second. Just give me a second. I have to import this book. Says that text one is not defined. Just give me a sec. Okay. There's a syntax for using this. I have already imported this. Okay. Just a second. Just a second. Just a second. Typically, I can access it like this. Okay, just a second. From NLTK dot book star. Can I use text one now? Yeah, I can now. Okay, so if you look at this book, text one, I want to show you the type of this book. This is going to be nltk.text.text. Okay, so it's a special NLTK text version. So this text version, if you want to tokenize, you can just directly do say text1.tokens and it will tokenize it for you. It will show you the entire book and each word is kind of segregated by using the word tokenize function. Is this clear?
Yes.
So these are all like if you want to read, you can read it like this. Okay, you can just print it, say separated by spaces. So essentially, it is taking that the text of the book and showing you individual words. Okay, so these are your tokens. How many words are there in this book or in this excerpt that it has taken? Okay, so around 2,60,890. Okay. So I'm going to take this book and I'm going to tokenize it. Okay, let's see this. I'm not removing any stop words or anything. Okay, I'm just simply tokenizing it. So it's already tokenized, but I'll be now stemming it. So this is like this. So I'll just do it like this. So let's say for each word in this tokens. Okay. Okay, for each word in this tokens, I'm going to say stem using say the Porter stemmer and the snowball stemmer. Okay, so stem each word. Okay, and essentially collect. Let me call it snowballed stemmed list and say Porter stemmed list. Okay, so I'm storing them. Okay, and I'll also store. I know. Okay, original words I know already. So this is Porter stemmed. This is your snowball stemmed. And then I will append them to this Porter stemmed list. Same thing I'll do for this snowball stemmed list. Okay, 1 second. Is there any mistake here? Sorry, I forgot the append. I forgot the append.
Oh, append. Okay.
Okay, so it's doing it. Okay, it'll take maybe 1 or 2 minutes. Okay, this is done. So once I have this lists, I'm going to show you in a data frame. Okay, so maybe I'll put the original words text1.tokens, give it some column names. Okay, so column names I'm giving as say original words. Say original word. Okay. So let's call this as maybe say data. And I will say data of my Porter stem. Okay, so this is Porter underscore stem. This would be my Porter stem list. Similarly, I get the snowball stem list. All right, so if you look at your data, I mean, you will not see right now any differences. Do you see any differences in these 10? No, right? The 10 words that are shown to you. In there, is there any differences between them? Like, look at Porter and snowball. Another?
Oh, okay.
No, but it's the same, right? Okay.
Okay.
So what I'm going to do, yes, what I'm going to do right now is I'm going to drop duplicates because there are words which are repeated, right, in a book. Yes or no?
Yes.
So I'm going to drop these duplicates. Okay, so the duplicates have been dropped. See, previously, if you remember, how many words were there? 2,60,000, right?
Yes.
Now there are just 19,317 words. Okay, after dropping duplicates. Okay, I'll do it in place. Because I'll just reuse it. So this is your data. These are the 19,317 words, and for each word I have the Porter and the snowball. Now I want to figure out where Porter and snowball are not the same. Do you see any differences, at least for the ones that are shown here? No, right? So you might
No.
think that they both are doing the same job. It's not. You might see at least 50 words, in my opinion, or 30 words for sure, where they are different. Okay. And you will typically see the results of Snowball will be slightly better than Porter. Okay. So I'm going to show you where these two are different. So look at data of Porter stem and print when they are not equal. Yeah, when they are not equal. Does this make sense?
Yes.
Okay, so I'm going to show you that they will have subtle differences. So these are the words where they are not the same. Okay, around 683 words are there. So quite a lot. Okay, quite a lot. Now, just by looking at it, can you see that Snowball is actually more complete most of the times?
Yes.
Porter
Mostly,
tends
sir.
towards like prefix, right? Incomplete English words. But Snowball can give you, I mean, the exact root also, the exact complete English word. So is this clear? Shall I go ahead? Okay, all right.
Yes.
So, I mean, if you get a chance, okay, if you get a chance, you use this directly. Okay, you use this directly. Snowball. All right, but people they use Porter and Snowball kind of in the same. Okay, because there is not much of a difference between the two, to be honest. Okay, 683 is not a very big number. Okay. Okay. So, I mean, if you would have found out all the unique words in this book, right? I could have done it. I do have the original words, right? Where are the in text1.tokens? Okay. So this is text1.tokens. Okay. I want to find out all the original words. So, okay, this is going to be a list. I have to maybe say I convert it to a data frame or say a NumPy array. Okay. And it will take some time. Do the unique of this. Okay. And getting the unique of this, after this, I'm going to find out the shape. So this will tell me how many unique values are there. Oh, I converted it. Just a second. It says that list object is not callable. I converted this to why it is saying list. Oh, sorry, it's this. Any bracket mistake is there? Yep. Okay, so we have a total of 19,317 unique words in this, and out of just those, like 683 are different. Okay, so how much would that be? Like 1%, like 0.1, 0.5% approx. So 683 by this number would be how much? 19317. Yeah, 3% approx. Around 3.5% numbers are different.
Yes.
So it's not a reasonable number to worry about. Okay, so these are the differences between the stemmers. Now you can see that even like in some cases, Snowball is also not giving you complete words, right? Like this, Melville here. I mean, I can show you, I mean, I can print all the words and you will see that Snowball doesn't, I mean, if you just print this data again, right, you will see that Snowball also doesn't always give complete words. Like this, retracing,
Yes.
it gives retrack. Okay.
Retrack.
Okay, so the idea is there another way in which we can get, say, complete English words? Yes, there is. And why do we want to use this? That's the first question. Or in which application do we want to use those? I mean, that particular way of reducing the word to its original word. So imagine that you're doing machine translation. Okay. Okay. Imagine that you're using machine translation. Do you think that you should, I mean, is there a need to preserve the parts of speech when you're doing machine translation? Is grammar important? Yes or no?
Machine translation, right?
You see, assume that if the machine is intelligent enough, okay, do you think that machine can recognize the mistakes that you're making if you would have used stemming.
Yeah, if the mission was that much intelligent, it can.
Like ChatGPT, right? ChatGPT
Yes.
does recognize, okay. But think about, say, Google Translate. Have you tried using Google Translate? So Google Translate is not a transformer right now. So maybe I can show you. Yeah, that is one way to. So translate.google.com. I don't know if they have deployed a transformer here. The last time that I checked, it was not working well. Okay, so let's say we say that. Okay. Okay, in what language? See, it corrects the mistakes, right? Currently, so I think they are doing some spell check also. Okay, let's say I do this. Okay, let's say this. No, it's still doing a good job if you think about it. Like it's taking care of the mistakes. So the idea is, I'll just write it like this. Okay, I go to home. Okay, I mean it still recognizes it. Yes or no?
Yes.
I was not aware that, okay, they have deployed a transformer here. So previously it didn't do any spell checks. Okay, whatever you typed, it converted it back to, say, another language. Let's say I converted to Arabic. I don't know, if anyone is here, maybe I'll use Hindi.
You can use Tamil or
Then you can tell me, okay, if the translation is correct or not.
yeah.
So let's say, where is this Tamil? Do you see anywhere? Telugu I see.
You can type such languages.
1 second. Yeah, it was there. Okay. And now you can interpret it.
It's doing good actually.
It's doing good. Okay.
Yeah.
Let's say. Still doing a good job.
Yeah, it's doing a good job actually.
Okay, but I'll tell you, like in some cases, that's good. I mean, maybe the models have become so much better. But I remember using it in around like 2 to 3 years back, and it failed miserably for most of the cases. I don't know if you have ever used it. Have you used it?
Yeah.
Has
I've
anyone
used it in college also. I had some.
Was it that good, like back then?
Yeah, no, not this much good. Even now it was recognizing this much.
Okay. So
That time the
what
spellings has to be very much appropriate.
So the point that I'm trying to raise is this, or the convey is this. See, when you are working with machine translation, grammar is important. Okay, that is one thing. Another is, let's say you are doing summarization. So don't you think, like, if you reduce the word to its say stem, the prefix that we used, do you think summarizer would work well if it does not support, say, dictionary matching? If it doesn't recognize what the grammar is. Nowadays, the translators that you saw just now, they are quite intelligent, right? So they can recognize what type of voice it is. I mean, is it passive, active, right? What verb it is, okay? Which form of verb it is, and so on. Yes or no?
Yes.
But let's say you are building it from scratch. So don't you see that, like, you need to give in complete words?
Yes.
Does that make sense or not? Okay,
Yeah.
you cannot give it incomplete words, right? If it doesn't support dictionary matching. So think of tasks like translation, summarization. Maybe think of tasks like generating captions. So let's say I give you a scene and you want to generate, say, a description of the scene. So the model would be learning from some pre-generated captions, right? So those captions have to be complete. You cannot pass in incomplete words. Okay, you cannot pass in incomplete words. That doesn't make sense. So see, for sentiment classification, my objective is not to preserve, you can say, the grammar, right? Yes or no? Do you see a subtle difference between sentiment classification and machine translation, which requires you to preserve semantics? Both of them or only one of them? Think about it. which requires you to preserve the actual semantics, like the relationships between the words. Like, see, okay, can you tell me what gets lost when you convert your data to tabular data set? What gets lost when you convert your data to a tabular data set? There is something which you are losing. Okay, let me ask you this. If I give you unstructured data, like if I tell you the first, this vector, okay, if I give you this vector, you can actually generate this tabular vector, right? This row
Yeah.
vector.
Yes.
But if I give you this vector, would you be able to generate the previous vector?
No.
So what is the thing that you have lost? Ordering. The
Yes.
relationships between words. The semantics are lost, right? How those words are connected. Does that make
Yes.
sense?
Yes. Yes.
So the idea is, for simple tasks like sentiment classification, I do not really need the semantics, the ordering, the relationships. I do not need those things. I only need, you can say, the root of a word so that I can reduce the features. Essentially, I need to know what that word is. See, can I say that when I'm doing sentiment classification, I'm only concerned about the keywords, positive and negative keywords? Yes or no? And
Yeah.
how many times they are repeated? So there is no preservation involved for your ordering, relationships, the type of verb. Okay. So all those things we really don't care about. Okay. We are removing the stop words. But for translation, if you remove the stop words, do you think it will work?
Stop words. No.
Yeah,
If the stop
it-
words was not there, then it'll
like
be incomplete.
everything would be lost, right? Semantics, everything, like syntax, like this relationship between the words, all of that would be lost.
Lost. Yeah.
So the idea here is, okay, for certain, you can say, type of tasks, you do require like the complete English word. Okay, even if you lose, say, the verb part of it, like if it is running, ran, runs. Okay, even if you use that part of it, like if I just give you the root word, let's say this is run, you will still be able to translate it. That's what you saw in Google Translate, right?
Yep.
Okay, I mean, I said I go to home, or maybe say I said I going to home, and it will actually correct it and will make it go. So parsers are actually intelligent nowadays, but the idea is I still need the actual word, right? At least I need the actual word. I cannot have an incomplete word unless dictionary matching is incorporated. Okay. Nowadays, the parsers are actually much more intelligent. Okay, so even if you give half-baked sentences, it will still translate. That's what we just saw. But if you were to build one from scratch, you need to have like the exact form of word being preserved. You cannot have incomplete words. So this is the second form, which is called as lemmatization. This is also used to preserve the words. Okay, so this is also used to preserve the words. Yeah, so I'll show you the differences with respect to stemming. I'll just create one here. Okay, let's do lemmatization. For this, you have to download WordNet. You have to download this WordNet. Okay, this is a default lemmatizer which is available in NLTK. Okay, so download this prerequisite package. Now, once you download this package, okay, what you have to do is you have to import this. So go to NLTK and import. This is called as WordNet lemmatizer. Okay, and you can just take this lemmatizer. Okay, and let's instantiate it. Say WN. Okay, and now you can start lemmatizing. Okay, so let's say if you want to lemmatize a word. So which words do you want to lemmatize? Give me a word that you want to lemmatize. Say running.
Yeah, running.
Okay, now see this. Okay, it will actually return running right now. Okay, it returns running right now. It should be run, right? If you think about it.
Yes.
Okay, there is a reason. It will simply return runs right now. Okay, no, sorry. Okay, I'll ask you this, okay? When you are trying to find the context of a word, what do you think is more important? Okay,
Context.
yeah, I'll talk about it. See, from the perspective of English language, if you look at the word running, okay, which part of the speech it is? Verb, right? Okay, and what is runs? Noun. Okay, so by default, okay, these lemmatizers have a part of speech incorporated in them. So if you provide the correct part of speech, it will, give you the correct lemma. So what lemmatization does is, it, you can say, converts the word to its lemma, to its original word, okay, to its original word. And this is actually much more precise. I'll talk about like even difficult examples. So let's say so by default, this is noun. So you see that, okay, it gives me running. Yes or no? I'll set it to n. So runs is noun. Okay, so it gives you run. Now think about this. If I pass a verb here, what do you think you'll get? If I pass a verb here, what do you think you'll get?
On running, right?
Run. This will be run. Okay. Does it make sense?
Yes.
Okay. So part of speech is very important when you want to lemmatize. Okay. Because in the context of a sentence, there might be various different meanings of a word also. We will also tackle those things. Okay. Do you realize that English is a very ambiguous language? Like one word can convey many different meanings in different sentences.
Yes.
Yeah.
It's actually very ambiguous, I would say. If you think of 10 words right now, I'm pretty sure you are thinking of one word which has multiple different meanings out of just 10. See, I'll tell you, okay, think of the word, let's say book. So
Yes,
book
book.
means that reading a book, you are booking a flight ticket. Okay. Think of word like report. A report is like you reporting to the boss, you are preparing a report. Okay. Think of words like bank. Okay.
Bank.
Monetary bank, river bank, blood bank. It means trust also. I bank on you, right?
Show.
Show also, right? You are watching a show. You are looking. Basically, it's a display. Okay.
Yes.
So there are many different. So whatever. So think of this 20 words. I'm pretty sure 2 or 3 of those words have different meanings in
Yes.
different contexts. Okay. It's very ambiguous. So the idea is we will actually do this a little later, like the disambiguity part, how to identify like the word disambiguity. We'll do this in more detail. But for now, let's just stress on this fact that part of speech is very important if you want to disambiguate. Yes or no? So if I say that I bank on you, what part of speech it is? Is it a noun? See, I say I bank on you. It would become a verb, right? I rely on you. This is like this, right? I rely on you. But
Yeah.
if I say that bank is a noun, then it would be treated as a monetary bank, right? Yes or no? Does that make sense? But if
Yes.
you say I bank on you, if you treat it as a verb, then it would be treated as, what we say is like an activity, right? That you're doing. So the idea here is we use these parts of speech to figure out the correct lemma of the word. And this is actually more accurate. You will always see that the words would be complete. So I'm going to just run this WordNet lemmatizer on. So first, let me show you how to get the part of speech. Okay. So in NLTK, if you want to get the part of speech, so there is this function called as part of speech tagger. So this also comes by default when you install this WordNet. Otherwise, it will not be running POS tagger. Okay. So
And
I
this
wanted to
POS
show
tag
you
will
this.
only run on lemmatizer, right?
It will, you only need it for the lemmatizer. You
Okay.
only need, but you can run it generically also if you want to know the part of speech of every word in a sentence. Okay. So what we have to do is you have to, so give me a sentence. Okay. Give me a sentence. Give me a
Currently, I
sentence.
have a class to attend.
Okay. I have a class to attend.
Yeah.
Okay, let's say this is a sentence. So I'm going to find the POS tag for every word. I have a class to attend. So the first thing that I have to do is tokenize them, right?
Yes.
Okay, so tokenize the sentence and let's see what this outputs. Do you see that what it is outputting? So for every word, it is printing I is what? PRP, it means a preposition. Have is a verb. It starts with a V. Okay. A is a determiner. Class is a noun. This two is just, I don't know what this TO means. There is a huge list for this. Attend is a verb. Okay. So let's see what are these letters, what are these tags. Okay. So there is a huge list. So what you have to go to is, I think you have to go to UPenn. Okay, one second. You have to go to nltk.upenn.tagset. I think there's a huge list. Is it? One second. Okay. Is it nltk.help.upenn.tagset? Or is it UPenn? Just give me a sec. Okay. There is a huge tag set which is present, which tells you this tag means this. So University of Pennsylvania developed it. That's why you see this. Okay. Do you see this anywhere? Yeah, here it is. This is the function. So this WordNet tagger was developed by University of Pennsylvania. So these are the different tags. Okay, there are quite a lot of it. So if you see all these symbols, okay, it will be marked as a $. Okay, if you see these quotation marks, it will be just marked as these quotations. Okay, if you see these parentheses, it will be labeled as this. Okay, if you see a comma, it will be labeled as this comma. Okay, and things like this. So I'll just go to the important ones. If you see a number, you will see that it's a cardinal. Okay, so any number of this format, it will just label it as a CD. Okay, DT is a determiner like a and the or and so on things. EX is existential, so basically there. FW is a word which is not recognized in English, so maybe German, English, French, Hindi words. Okay. In is your preposition, conjunction. Okay, so like this, astride, among, upon, whether, out, and so on. J is an adjective. This is important. Adjective starts with a J. Okay. So then these are some adjectives which are listed. Then you have comparatives. Comparatives are those adjectives when we are using to compare two things like bigger, brighter, lighter, higher, shorter, taller, things like that. Then you have these superlatives. So superlatives are, you can say, the highest form of a verb, like highest form of the adjective, like cleanest, crudest, largest, tallest, smallest, okay, deadliest, commonest, okay, all these things. If you have a bullet point or a marker, it will say it as ls. Then you have modal auxiliary. I mean, the important things are you should focus on the nouns. So nouns start with an N, okay. You have a proper noun, you have a plural noun, you have this, what is this called as? So NNS, okay, just a label. So this like undergraduates, scotches, products, okay, Amazonians, okay, fragrances, averages, and things like that. Okay. PDT is a predeterminer. So like these, okay. So the important thing, what I'm saying is, see, if it starts with a P, it's a pronoun. If it starts with a N, it's a noun. If it starts with the R, it's an adverb. If it starts with a V, it's a verb. Okay, let me just show you. If it starts with a V, it's a verb. Okay. So important things to remember is J is an adjective, R is an adverb, V is a verb, N is the noun. Okay, is this clear? I mean, you can go through this entire tag set. Okay. All right. So once we have this tag set, okay, I know, okay, what tag constitutes what. So I'll be using this to lematize your each word. So I'm going to make a small function. Okay. So let's call this as a WordNet tag, because see, currently when I use this lematize function, I'm passing a single letter to it, right? Yes or no? I'm not passing NN, NNP, NNS. Yes or no? Does it make sense? I'm passing a single letter, the very first letter. If it's a noun, I pass a N. If it's a verb, I pass a V. If it's an adverb, I pass a A. Sorry, if it's an adjective, I pass a A. Okay. So if it's a pronoun, I pass a P. So those are the things that you have to pass. Okay. So I'm going to get the WordNet tag, or you can call it say get POS tag from the WordNet tag. Okay, from the WordNet tag. Okay. So let's call this as WordNet tag. Okay. So if your WordNet tag, say it starts with, let's say if it starts with say n. So if I just do it like this, if it starts with an n, what do you think I should return? Small n? Does that make sense? If the very first letter of any noun, see nouns have many NN, NNP, NNPS, they are all nouns, right? Yes or no? Do you see this? So if I use this WordNet tagger, I will get these things, okay, just like this, NN, NNS. So when I'm going to lematize, I have to pass a single letter to it. So I'm just checking if I get the POS, the WordNet tag as a N. Okay, my POS would be this N. If it starts with N, my POS should be just this small n. If it's okay, so I should just remove this. Okay, just give me a sec. I'll just copy this. Okay, else if say if WordNet tag of 0 is say a verb, I just pass this capital V. Else if I have say a J, which is an adjective, I pass this an A here. And so let's say I'll just do it for one more. Maybe say it's an R, it's an adverb. Okay, let me just see what this POS tagger takes. Okay, NLTK. WordNet lematize. Yeah, here it is. Do you see any POS anywhere? Yeah, here, these are the valid options. These are the valid options that you can pass. So these are the valid options that you can pass for POS. So this is N for nouns, V for verbs, A for adjectives, R for adverbs, and S for satellite adjectives. So these are okay, the possibilities. So if it's a adverb, I just pass a R again. Else I just pass a noun. Okay, else I just return a noun. Everything else is by default a noun only. Okay, so I'm just passing this as a noun. Okay, satellite adjectives I'm ignoring for now. There is a equal to equal. My bad. Okay. So the function is ready. Let's see. So this is the sentence that I have. Okay. So these are the POS of the sentences. Okay. I'm going to run a simple for loop. So let's say for J in, can you give me like a different sentence where can you give me a different sentence where I can see actually, okay, if I lematize it, because if you see the lemmatized version of these, it will be exactly the same. I have a class to attend. Yes. Give me another sentence. Okay, so let's say I have been running since a long time. Okay.
Time. Yes.
Okay, since a long time. Okay. Okay. Like for a long time instead of set. Okay, so basically it should just trim this running to run, and everything else should be the same, right? Yes or no?
Yes.
So I'm going to show you this. So let's print J. So first it is just tokenizing every word. Do you see that it just tokenizes every word?
Yep.
Okay, and now what I'm going to do, if you look at J of 0, can somebody tell me what will this print?
The first.
This everything. I have been the words. Okay. Look at this. It prints only the words, right? If I do JF1, it will print the tag that is generated. Does it make sense?
Yep.
Okay. So for each word, this is the word. Okay. This is the actual word. Let's print, say, okay, this is the word. Okay. This is your word. I'm going to print this word first, and then I'm going to print the lemmatized. So this was the lemmatized version I want. So lemmatized version is given with the wn.lemmatize. And this is the part of speech. So let me use this function on this part of speech. So get POS tag from this J of 1. Does it make sense? So I'm passing this part of speech, okay? And so it's wn.lemmatize. Okay. So pass this word and the POS tag, okay, and the POS tag. And this should be appended to this POS. Okay. I think that this makes sense. Let's see. There is a bracket mistake here. Okay, do you see that? Okay, let me just make a here. Okay, let's say this is the lemmatized word. It's doing the job correctly if you see carefully. Let me just put, say, some brackets here. Do you see this?
Yes.
Okay. So only run have been, lemmatized. Running has been lemmatized to run. Everything else stays the same. Okay. So this is how you can use this lemmatizer. It is quite useful. Okay. What do you think the lemmatized version of, and it always will give you complete words. What do you think the lemmatized version of this would be? Let me just ask you this first. What do you think the origin word is for worst?
Origin.
Was only.
No. What is the origin word for this? See, worst is what? A superlative, right? Yes or no? See, if I say that, okay, A is worse than B, it's a comparative, right?
Yes.
What is the original word? Worse is a comparative. Okay, worse is a comparative. Worst is a superlative. What is the original word? Okay, think about this. Big is the word, bigger is a comparative, biggest is like the superlative. So what is the origin word for this worse and worst? Anybody?
Verse.
No, you cannot say. See, when you are describing that, okay, you will not say that you are worse, right? You never say that. What do you say? You are?
No, worst.
No. You are worst, meaning that essentially you are giving him the highest degree, right?
Yep.
He may not be the, see, let's say there is a topper of your class, okay? So you will say that you topped the class, right? That is like the superlative thing that you can do, okay? So if he was a mediocre, bad, it's actually bad. So when you say that you are bad, we never say you are worse, right? Worse is always a comparative. You compare two things. A is worse than B. Yes or no?
Yes.
If you are saying that you are worse, which means that you are grammatically incorrect, sorry. Okay. So in this case, worst is what? I mean, am I passing the part of speech right now? No, right? So what is worst right now? It's a adjective, right? It's an adjective or a verb? It's an adjective only. It's a superlative. Do you see that?
Bad. Okay.
By default, it is a noun, right? You have to pass the part of speech. Okay. So don't think that, okay, it will always convert it to its root. So lemmatized word can be actually very different from the prefix. So it is not necessary that the word would start from the same prefix. But don't you think it makes more sense? It makes more sense, right? In comparison to your stemming,
Yeah,
where you always have the prefix there.
Yes.
Okay.
Yes.
Maybe a little bit of phonetics are also there, but you will always have the same prefix, right? Here you will not see the same prefix. Okay, it might be different also. Most of the times it will be the same. I mean, the origin word, but it can lead to a different word, so don't get confused. Okay,
So
I'll
that's
stop.
where,
Yes,
semantics is required means in certain cases there only lemmatization is
lemmatization is important. Yes, wherever you want to preserve the semantics, then you use this. Okay. So, which do you think is more expensive, lemmatization or stemming?
Expensive.
Which do you think is more expensive, lemmatization or stemming?
is it lemmatization?
It's lemmatization, right? Because I need to compute part of speech, and then I have to pass the correct part of speech, right? Yes or no?
Yep.
In stemming, do we require any part of speech? No, right? It just directly converts it to its original stem or original prefix.
Yes.
So lemmatization is much more expensive. So I mean, be cautious of what you are using. We are doing it on one single sentence right now, so you are not seeing that much of an impact. What if you had to work with, say, 1,000,000 documents or 1,000,000 paragraphs? Then it would cause chaos. Okay, so be careful of like what you wish for and use it appropriately. Okay, lemmatization is very expensive in comparison. Okay, I'll stop here. We'll do more applications in the next class. Okay, so this was just to introduce to you. So we actually talked about representations only. Okay, and what we say is tokenization, basically different stemming and lemmatization.
Yes. Stemming and lemmatization.
Okay, I was planning to cover some EDA also. Like basically given some text, what can you extract from it? Okay, so we will do this in the next class maybe. Okay. All right, I'll stop here. Let's meet tomorrow. Let's try to finish up the remaining applications. And there is a one question here in the chat. Yes, Shilpa, if you have some questions with Plotly maps, yeah, you can ask. But can we do it tomorrow?
Okay, no issues.
Can we do it tomorrow? Okay.
Yeah.
If it's not that urgent, I hope. Okay.
It's related to the Captain project only actually. Like,
Oh, okay. Then I would not assist in this case.
okay.
It is not right then, right? Because you have to do it individually. See, if
Yeah,
I
like
give you
I'm almost done. There's just this map also.
okay, I recommend that you try using ChatGPT. Okay, and see with the explanation that it gives you. Okay, see if I help you with this directly, then there is no point in it,
Okay.
right?
Like I've
And
been trying with that since long and tried to search for it also, but there are some parameters which are to be
Yes.
my
See, I also need to search. Okay, it's not that I don't have to. I don't remember all the syntaxes, right? You see that I've been struggling with NLTK quite a lot. Yes or no? So it's see for sklearn I'm quite comfortable because I use it very frequently. NLP I don't use it because I use more advanced libraries. NLTK is still a fundamental library. Okay.
okay.
So for Plotly, I don't use Plotly at all. See, sorry, Kiran, you said something.
Like I think we can find some answers in the GitHub also for the solution.
Yeah, for sure. See, the thing is, what I want to convey here is this: for all these libraries, right? You don't really have to remember the syntax. Okay, when you are going for an interview, right? They will give you access to internet, so they'll give you a task. See, at least basic constructs you need to write. Yes or no? If you don't write that, then they would not appreciate it. So you should be able to write basic constructs like the basic Python syntax, and then if you need some additional plotting, say like basic matplot scatter plot, you should all be able to do that. Like in Plotly also, you should be plot simply. But then if you want to tweak some hyperparameters, maybe say change colors, change marker size, and all that, then you need to know the arguments, right? And not everybody knows it. There are so many libraries that you're dealing with. So don't worry too much on that aspect. Okay.
Got it.
Okay.
And Shilpa, if you don't mind, like what is the project that you're working on? The phone papers, right?
It's a
Okay,
common for
okay.
everybody.
Yeah,
Yes,
yeah,
it's
it's
common
common
for
for
everybody, I
everyone. And
believe.
I think today is the deadline for submitting, but I haven't
Yeah,
even.
that's what like this. Today was the last point, and I could not get one of my answers, so I just wanted to.
Okay, but
It's okay, Shilpa. I mean, there is no harm in it, right? Like, even if you're unable to do one of the things, right? Maybe spend some time on your own. If you are
I'm
still unable
able
to do it,
but visualization part is not looking that attractive and good.
oh, see, for that, then you need to probably spend a lot of time in learning the advanced stuff with these libraries.
Yes.
Okay, so Plotly and Seaborn you should explore. Seaborn is actually very visually appealing.
Okay.
Okay, maybe try the same thing with Seaborn. Okay, maybe try the
Functionality
same thing with
actually,
Seaborn.
but like I wanted the maps to be in 3D and all, so that part I
Okay, okay. If you are interested, you can explore libraries like Bokeh and Data Shader. Okay, those are advanced libraries. They are interactive, so you can actually play around and I mean, basically, put your cursor on the plot, and it will tell you what the exact value is where your cursor is at. So you can make interactive plots like these with Bokeh and Data Shader. I think Matplotlib also supports some of it, but you need to have those interactive plots.
that over data where I can just put my cursor.
Yes. So if you want to do that, right, you need some advanced plotting libraries for it.
Yes.
Even Matplotlib supports it. Okay, but then you need to know the exact function. It's called as, I think, iPlot or interactive plots, something like this. Okay. Do search for it. Yeah.
Project they give it very specific that you have to use Streamlit, you have to use Plotly.
Oh, okay. I don't think anybody would go in that detail. But if you want to use like even a better visualization, go for it. Okay. I don't think people will be sticking to that specific library if that's what they are asking for. Okay. One or two questions you can do in other libraries also. You can say that, okay, I found that to be easier and visually appealing. Okay. So no harm with that. All right, guys, I'll stop here. We'll meet tomorrow and we'll do the remaining applications.
sure, Santan.
Bye, everyone. Take care.